All right, let's get started. Thanks for coming, everyone. So kind of continuing in this theme that's been going on in this room of identity, we are going to be giving kind of an overview, kind of taking a step back at container and workload identity in Kubernetes.
I'm Mike Denise. I work on the GKE security team. I've worked primarily on identity out here in Seattle. I am also the co-chair of the Special Interest Group for Authentication in Kubernetes.
And I'm Spike Curtis. I'm a senior software engineer at Tigera. I'm also a longtime contributor and core maintainer on Calico, and I co-chair the Istio security working group, and I am a maintainer of SPIFFE standards. And those last two, Istio and SPIFFE, we're going to be covering in a little bit of detail later on in the talk. So this is a talk about workload identity, so it's probably worth taking just a few moments to kind of make sure we're all on the same page about what we mean when we say this phrase, workload identity. So what we mean by a workload is an instance of running code that does the work of your application. So we're not talking necessarily about code that provides your platform or code that that runs your infrastructure. Workloads are the bits of your application that are running in your environment talking to each other. And so in Kubernetes, a workload is typically a pod. To get a sort of unique identifier for a pod in Kubernetes, that's the name and namespace. You're also often interested in what code is being executed for your workload. And so for Kubernetes, that's the image name or the image SHA. And lastly, you're often interested in extra kind of identifying information about the workload, like what kind of environment is it running in? Is it dev or prod? What application is it attached to? Or other kinds of configuration. And for that identifying configuration, the sort of affordance that we have in Kubernetes is labels for that kind of identifying information. And this talk is going to be not sort of about like what is the data that makes up a workload identity, but more about how workloads prove their identity in a cluster. So in particular, we're interested in kind of three use cases, sort of generally speaking about this. So we're talking about proving identity over a network. And one of these use cases we're not going to cover because it's pretty well taken care of in Kubernetes. And that use case is how a pod connects to the Kubernetes API server if it needs to access Kubernetes itself and proves its identity. And for that, we have service account tokens. So the two use cases that have been kind of a gap in Kubernetes are pods being able to prove their identity to other pods in the application so that they can get access to services or resources, and pods being able to sort of export their identity to external systems. So maybe you're running Kubernetes inside of a public cloud and you want to get access to some of the managed services that cloud provides, like say Bigtable or some other service, and you want only a particular subset of the pods in your cluster to have access to those services or those resources. You want to be able to prove who those pods are when they make that connection. Or maybe you have a third-party service that you're using that has nothing to do with the provider of your infrastructure, but you still want to be able to give differential access to different parts of your application. Maybe only one pod actually needs to access that data, or only one pod needs to actually access that service. All right, I'm going to hand it over to Mike to talk about desirable properties.
So I want to get into desirable properties that you might want to consider when picking an identity solution for Kubernetes. So these are some very high-level properties that you want to consider. They're actually fairly complex, so I'll try to summarize them quickly. So strongly authenticated, what does that mean in this context? So strongly authenticated to me means unforgeability. So we want to pick in to strongly vet and thoroughly vet any attributes that we place inside the identity assertion, and we want to pick a communication protocol for communicating this assertion that does not compromise the security and certainty of that identity proof. So prevent escalation. We want to be aware of the security boundaries that exist in Kubernetes today. For example, we wouldn't want a node compromise to compromise all identities in a cluster. So good user experience. This is about removing hurdles or barriers to adoption. We want our identity solutions to be easy to deploy and operate on Kubernetes, and we also want them to be easily consumed by application developers. Performance and availability. Kubernetes is designed in a way that if the control plane goes down, the data plane coasts. We don't want to undo any of that hard work by taking a strong dependency on the control plane to perform workload-to-workload authentication.
So what we'd like to do in this talk is give a kind of high-level overview of four options that you might want to consider if your goal is to establish this kind of workload identity in your applications. This is by no means an exhaustive list, but a good place to start in terms of what's available to you in Kubernetes and in some projects that are designed to work well with Kubernetes. So we're going to talk about the Kubernetes Certificates API. We're going to talk about the sort of new and improved Kubernetes Service Account Tokens. We're going to talk about Istio, and then we're going to talk about Spire.
So to start off, we're going to talk about the Kubernetes Certificate API. So Kubernetes has native support for some certificate provisioning flows. These were actually originally introduced to support kubelet TLS credential bootstrap. However, they were designed to be general purpose, and they're actually useful for workload-to-workload identity. The entire provisioning flow is made up of a series of controllers communicating through the API server. It follows the model of Kubernetes control processes. So let's dive in and understand how this provisioning process works. So the first step of the provisioning process, the pod generates a key locally, builds a CSR, and submits that CSR to the Kubernetes Certificates API. Then an approver observes the pending CSR. It does some authorization checks, and we're going to dive into what those actually mean in a couple slides. And assuming the authorization check passes, it approves the CSR. Then another signer observes the newly approved CSR. It signs a certificate and uploads that back to the Kubernetes API. The pod then downloads its certificate and uses that certificate to authenticate to other applications. So what in this entire flow are you responsible for if you're using the Certificates API for workload-to-workload identity? It's these components. So you're responsible for linking in SSL libraries to your pod and any relying party so that they can communicate and authenticate client TLS. You're also responsible for this approver component. So this approver component is the gatekeeper of the certificate API. It decides whether or not certificates are signed, so it's actually a fairly high privileged and sensitive component. At a very high level, this authorization check can be divided into verifying two requirements of any CSR. So the first requirement that we have is that a workload is the origin of the CSR. So what this means is we don't want workload A to be able to submit CSRs for workload B. The second requirement is that the workload is authorized to act in the request context. So what that means is if workload A is requesting to serve service B, we want to make sure that it's authorized to do that. We want to make sure that it's standing behind that specific service, or we want to make sure that any extensions that it has or any usages that are specified in the CSR are authorized extensions to be allocated to that service or to that workload. So once those two are satisfied, we can then go ahead and approve the CSR for later signing by the signing controller. So that's a very high level view of the requirements of the CSR approver controller. However, since this is an asynchronous control loop, it is free to do anything out of band. It can do the challenges that are outlined in the Acme spec that Let's Encrypt does, or it can wait for a approver manual intervention by maybe an operator. So really it's up to you on how you satisfy or how you decide these two requirements are satisfied. So that wraps up a summary of the certificate provisioning flow. It's really flexible and pluggable. However, it does require a bit of upfront work to build that approver and to retrofit your workloads to be able to consume the certificate provisioning flow. So the second option that I wanted to talk about today is the Kubernetes Service Account Tokens. So these have been around since pre-1.0 Kubernetes. So many of you are probably familiar with them. We've actually done a ton of work on them over the last three releases or so that make them generally useful for workload-to-workload authentication. These are actually useful in circumstances where client TLS breaks down. For example, these tokens can traverse L7 proxies, which make them often useful for communicating to external systems like AWS or Vault. So at a high level, this is the diagram of the provisioning flow for tokens. It's pretty complex, but the key takeaway is that the kubelet, upon starting a pod, will request a token for that pod. It exposes that token to the pod via a volume. The volume can then, the application running inside the pod can then read the token from that volume and present it to applications. The kubelet is also responsible for refreshing that token and making sure it stays up to date. However, I'm not going to step through this flow because as a user and consumer of the token APIs, this is actually all you care about. The pod reads the token from disk and presents the token to other apps. So let's look at the first half of this, the client-side part of this diagram, the token volume config. So this is a config for a token projection. All you have to specify is the path that you want the token at, the audience of the token, and the expiration of the desired expiration or TTL of the token. If we zoom out a little bit, this is an almost valid pod spec. Here we're asking for the projection, which is in the gray area at the bottom of this config, to be injected into the pod at var talk to spike token path. So all the application has to do is periodically reread from that path and use that token in a bearer token header. So part two of this diagram, what does the other app have to do? What's its responsibility? So that other app is responsible for token validation. And to understand token validation, let's take a closer look at the token that we're sending around. So the Kubernetes token is a JOT. It's a JWS, so it's a signed JOT. It contains the standard JOT claims like subject and audience. It also contains some Kubernetes-specific metadata. It's OIDC compliant as an ID token, so it can be verified like any other OIDC ID token. If you are running inside the cluster, we also expose an API from the API server called the Token Review API. So if this is easier for you and you don't want to worry about validating JOTs correctly, you can implement a flow where the pod presents a token to the other app. Other app performs a token review with that token. The Kubernetes API server will then validate the JOT and return authentication info contained inside the JOT. The other app can then freely apply authorization to the authentication info, and if authorization checks pass, return a response. So this is great if you're running inside the cluster. Some drawbacks to it. It's a dependency on the control plane being up in order for workloads to do authentication to each other. And it's not available everywhere. Like I wouldn't expect AWS to call into your Kubernetes cluster to do a token review. So that's some downsides. The Kubernetes API server also does some extra validation beyond a normal OIDC validation. It actually does verifies that the pod that the token was provisioned to is still running. And this implements a form of token revocation where you can delete the pod, and any tokens allocated to that pod will be invalidated. So to summarize this option, it's a more fully managed solution. However, it doesn't solve server authentication like the certificate identity provisioning could have. So now I want to hand it over to Spike to talk a little bit about Istio.
So the mechanisms that Mike just talked about sort of rely on your workloads kind of understanding that they're running in Kubernetes and calling Kubernetes-specific APIs to get their identity information and to use the identity information that they get. What I'm going to talk about are a couple of ways to do workload identity that are kind of built to run on top of Kubernetes, but don't take a hard dependency on Kubernetes itself in order to work. So the first one is Istio, and Istio is a big project. It does a lot of things, and workload identity is kind of one small corner of it. So I want to sort of preface this discussion of Istio to saying that we're taking a little tiny piece of what Istio is, and if you're interested in that, there are other talks and lots of documentation about Istio. And so with respect to workload identity and security, really we're talking about being able to do this use case of a workload talking to some other workload, or a pod talking to some other pod inside Kubernetes. And Istio is going to handle not just that identity provisioning, but it's actually going to handle all the way up through secure encrypted communication. So what Istio is designed to do is inject Envoy, which is a proxy, into your pod. So it'll be running alongside each of the workloads. And that proxy then transparently intercepts all the traffic that your workload is sending. And it can then sort of upgrade all of your traffic to talk over mutually authenticated TLS. So you don't have to make any application changes. You can just insert Istio into your cluster and have Envoy running, capturing your traffic, and sort of upgrading that connection from plain text that your application might be speaking to mutually authenticated TLS. So by mutually authenticated TLS, I mean that both the client checks that the server certificate is valid and is who they think they should be talking to, and the server checks the client certificate and that it matches who they think they should be talking to. So you can do this basically transparently. So the certificates and the keys that go along with them are provided to Envoy via Kubernetes secrets. And Istio has a component called Istio Citadel, whose responsibility is to mint and refresh those certificates. The certificates are tied to Kubernetes service accounts, sort of like the service account tokens that Mike just discussed. So you sort of provision identities in your Kubernetes cluster by creating service accounts and associating pods with those service accounts. And then Istio sort of handles the rest of actually getting you that mutually authenticated TLS connection. So this sort of is kind of contrasting to the Kubernetes certificates API, which is very flexible, but requires you to do a lot more work to actually get to that end goal of having mutual TLS connection. The other project that I want to talk about is Spire, and we actually just had a talk about Spire, and I'll be able to cover it in a little bit of detail, but there's also another talk tomorrow at 1:45 if you're interested in a more deep dive on Spire. So Spire is a CNCF project, and it implements SPIFFE standards. So SPIFFE is the secure production identity framework for everyone. And SPIFFE is basically trying to design platform-independent APIs and specs for workload identity. So Spire implements SPIFFE APIs, and this allows you to do kind of both of these use cases that we're concerned about in this talk, both workload-to-workload communication, where you can easily provision TLS certificates and then set up TLS between your workloads, or JOT tokens, which can be useful for taking some identity inside a cluster and making a proof of that identity to something outside the cluster by providing it with a JOT that it's able to verify independently. So as I said, SPIFFE is this set of APIs. One of the APIs is called the Workload API, and this is the primary API that your pod is going to use to communicate with Spire. So instead of talking to the Kubernetes API and using kind of Kubernetes-specific idioms to get TLS certificates or JOTs, you can use this platform-independent mechanism, which can be useful if you have workloads that are running outside of Kubernetes or trying to build kind of an identity system that can span your entire organization if you're not all kind of in on Kubernetes. So for TLS certificates, this is pretty straightforward. Your pod wakes up, it knows a well-known Unix domain socket endpoint and asks that endpoint for a certificate over a gRPC service call. And the Spire control plane responds with a certificate and private key that it should use. And that's basically it. Spire will automatically push new updates to your certificate before your certificate expires. So you just need to keep listening on that API, and you'll get new certificates that you can roll over to before the ones that you have expire. If you want to do JOTs, it's also over the Workload API and pretty simple. The pod wakes up, it says, give me the JOT that represents my identity, also passing along the audience that you want as part of the JOT. And then the control plane sends you the response, which is now a bearer token that you can put on requests. And if you are a workload that's trying to validate JOTs, you can either use standard JOT libraries, sort of in the same way as Mike just talked about for Kubernetes, or there is this endpoint on the Workload API that you can just hand it a JOT and say, please verify this JOT for me, and it'll send you back the authentication info, including whether or not that JOT was valid, and if so, what claims can we extract from that JOT that tells me about what that workload was. The last thing that we want to do is kind of give you some high-level advice about how to maybe choose between these different options. And I want to sort of preface this discussion by saying this is not the sort of end-all kind of opinion about what you should use, more of a starting place to kind of tell you where to look and get more information, because there are more of these systems than can fit in a 30-minute talk. We haven't really been able to dive into how these things stack up in terms of the desirable properties that Mike was talking about at the beginning. So with that said, thinking about what your use cases are, if your primary goal is to get this kind of secure communication from an application pod to other application pods in your cluster using TLS, then you can use the Kubernetes Certificates API and get those TLS certificates. If you want to control very carefully what are in those certificates and how they're approved, or if you want a kind of more fully automatic system, especially if you're kind of bought into the rest of the value that Istio is going to provide your cluster, then Istio is a great solution for this use case as well.
So for the second case, if you're interested in authenticating to external systems such as Vault or AWS or GCP, we recommend that you use Kubernetes Service Account Tokens. So these go where some of the other peer authentication mechanisms can't go because they can traverse L7 load balancers. They're also, verification is also built on standards, and these standards are actually already supported by many external systems.
And lastly, if your use case involves either multiple Kubernetes clusters that you need to federate the control over these identities, or if you need to do both pod-to-pod communication and being able to use JOTs and get out to external entities, or if you're concerned about kind of tying your identity system too closely to Kubernetes itself, if you have other platforms that you want to be able to control identity on, then the SPIFFE standards are a great solution for this. And of course, Spire is the CNCF project that is sort of best implementing these SPIFFE standards. All right. That is all we have. What questions can we answer for you? We've still got a few minutes.
Thank you.
Yeah.
The CSR API in Kubernetes and Kubernetes itself doesn't support certificate verification. So this kind of problematic thing.
It does not.
Right, so the question was,
Yeah.
do any of the, I guess, are you asking specifically about the Kubernetes certificate API or all of them?
The CSR API.
Okay, so the question was, does the Kubernetes certificate API support revocation?
The Kubernetes certificate API does not support revocation. What was that?
Yeah, I mean, there is no way to revoke those certificates once you have generated them.
Correct, that's the current situation. So the Kubernetes certificate API does not support certificate revocation. I think in general, my recommendation would be signed certificates for very short durations. That gets around some of the long-term issues you might have with leak certificates. 2 days is a lot better than a year. But yes, that is currently unsolved. There's open issues. We're just looking for the right solution.
Yeah. Yeah. So the question was, what is the best pattern to integrate with enterprise PKI? I think that Istio's story here is pretty good, which is that if you have to issue an intermediate CA certificate and then sort of delegate that to Istio. So Istio will still be signing, but it can be an intermediate CA in the kind of rest of your TLS hierarchy. I believe Spire also supports that mode where you issue an intermediate CA. Does the Kubernetes API?
Kubernetes root CA that is used to provision kubelet identities should probably exist one per cluster, so it does not mesh well with a company-wide PKI. And that's because kubelet identities are currently unscoped. They're not scoped to a single cluster. So the recommendation right now is to have a single CA hierarchy per cluster. However, that might change depending on if people have time to fix that.
Yeah, and I will say that both Istio and Spire are on their roadmap is support for not just having sort of intermediate CAs, but actually completely delegating the signing task to another program like Vault or your own enterprise CA. Yeah.
Does Spire support other XPIDs than X590?
So the question was, does Spire support any SVIDs, which is SPIFFE verifiable ID documents other than X509? And the answer is yes. Spire also supports the kind of newly spec'd JOT SVIDs. So that's the JOT use case that I was talking about. We actually have SPIFFE standards for that type of SVID.
So, a year or two from now, which of these options do you see being the most widely mature, actively worked on, and to put it quite bluntly, what would you put your money on? Especially, yeah.
I'm gonna get into so many fights if I answer that question.
Oh man.
It's okay, but you think this is a serious concern.
So the question was, in 2 years, what is going to be the most mature and widely adopted?
Yeah. So I think that it's a pretty safe bet that Kubernetes itself is going to be supported and adopted. So those Kubernetes APIs are pretty safe. Istio also feels like it has a big kind of not just a single company kind of behind it. So Spire right now is kind of the newest kid on the block and is starting to get some community behind it, but is still largely, I think, being worked on or invested in by a single company. That's not to say that they're not going to move on that, and they are now part of the CNCF. So I think it may not be the safest bet from our position today, but that doesn't necessarily mean that it won't kind of become this like widely kind of community supported project.
I will also say that the core Kubernetes primitives are not designed to be fully featureful. They're designed to enable bootstrapping featureful systems on top of Kubernetes as they're designed as extension points for something like Spire and Istio to sit on top of.
Do you see within that core functionality the ability to handle this well with federated or multi-cluster?
Yes, that's definitely a consideration. The question was, will this core functionality enable multi-cluster use cases? And the answer is yes, that is definitely always a consideration. And I think it's already enabling multi-cluster in Istio 1.1, which depends now on the service account tokens to bootstrap trust into their Citadel certificate authority. So yes, it is a consideration always.
Yeah.
Is anybody planning on working on delegation?
So the question was, is anybody planning on working on delegation?
I think that Spiffy had talked about delegation for a little bit. We've talked about it a little bit in the context of Kubernetes. The one issue with delegation is it's often modeled differently per identity system, and it's not an identity-focused. It's not entirely identity. It kind of is both authorization and identity. So there's like weird sticky things where you kind of want an employee to deploy a job, but if that employee changes teams, you want that job to keep running. So it's like an authorization check at a point in time that grants some permission that might be renewable, and it's very sticky and complex, and sometimes depends a lot on how you want to use that delegation. So we might design one for Kubernetes for the asynchronous control process flows. I'm not sure if it'll be generally useful. We are thinking about it in the context of Kubernetes, though.
Yeah, and we have those conversations in the Istio security working group. I don't think there are concrete plans yet about what we are going to do there. And same thing with Spiffy. The topic kind of comes up, but we don't have concrete plans at the moment.
Yeah, there's end user, for example, there's end user delegation. Delegating end user authority through a stack of services, that's an entirely different problem than the Kubernetes control process problem. So yeah, it's very nuanced and hard.
Yeah. So the question was, can we go back to the approver's duty slide? Did you just want to get a picture of it, or did you have a question? Before this one?
Yeah. What is the other apps? How do they validate that certificate?
Yeah, that's a good question.
So the question was, what are the other apps? How are they validating the certificate?
So Kubernetes, through its service account token mechanism, actually distributes the CA cert of the cluster to every pod in the cluster by default. So that CA cert exists on disk somewhere unless you turn it off. So the pod's client certificate will be signed by a CA cert that lives inside the container.
So this can't, this says that the cert was signed by the cluster, not specifically scoped to the pod.
So the cert. So the question was whether this is asserting that the certificate was signed by the cluster and whether that's scoped to the pod. And so it sort of depends on how you're assigning identity in this system, right? So you're responsible for writing this approver. And so the pod will send a CSR that has an identity attached to it, and then your approver has to decide, should I sign that certificate? And then If you do sign it, then that pod can now act as that identity. So you might scope that identity down to just the pod. You might scope that identity to an entire microservice. You might scope that identity to a particular DNS name, et cetera. So whatever scope you have approved, that's what the pod is going to be able to prove to the referring party or to the other apps.
And that certificate changes up to a cluster-wide root. And that root certificate, the public part of that, is distributed in all pods. So you just validate the certificate chain up to the root, and the root is available everywhere.
And that's just standard TLS or SSL library stuff. You just put this CA in and then say, okay, here's my certificate, please validate it. Yeah, so the question was if I want to allow a specific pod to talk to me, I have to build that in. And in general, what we've been talking about is identity. There's a whole separate question, which is authorization, right? The identity question is like, is this thing that I'm talking to what it claims to be? And that's the identity question. But there's a separate question, which is, are they allowed to be doing what they are trying to do? And that's authorization. And you can't really get a good authorization decision without the identity piece first, and that's what we're focusing on in this. Yeah.
For this one here, how does the approver get any information it can rely on?
So the question was, how does the approver get any information that it can rely on to make the decision? So the approver can do stuff out of band, and there are lots of interesting things that you could do. You could do TPMs, you could do all kinds of interesting out-of-band stuff. But just out of the box, though, the CSR gets marked by Kubernetes itself with the service account of the pod that submitted the CSR. So if all you want to do is tie a certificate to a particular service account or pod, you can just read that information out of the Kubernetes API server.
We record the authentication information on the CSR creation.
Yeah. Yes.
Once a CM gets compromised, do we have a mechanism to reconcile the secrets and re-inject new authority or not?
So the question was, if the CA gets compromised, do we have a mechanism to regenerate secrets and kind of recover from that?
So in this certificate flow, we didn't actually use any secrets. So we don't actually have to modify any data in etcd. I think that process would look like provision a new CA, add both CAs to the bundle, wait a little while for all the applications to reapply for the process. And once everybody has a CA, a certificate signed by the new CA, you can remove the old CA from the bundle. There's no automation for that. That's a very painful process.
And there was a question in the back there. I'm sorry, I can't hear. Okay, so if I heard correctly, the question is how do I see the future, or how do we see the future of multi-cluster identity, and whether we imagine that there's going to be a kind of hierarchy of assertions kind of back to a root. And I can answer kind of from the perspective of our discussions in SPIFFE. The answer that we kind of have settled on in SPIFFE is that you create different trust domains. Maybe you associate those with clusters, or maybe you associate them, we can put multiple clusters in a trust domain, but there's one kind of control plane that's issuing identities for that. And the sort of root of trust for that control plane is a single certificate, and it doesn't have to be part of a central hierarchy. And then we have SPIFFE APIs that allow you to federate that trust and basically say, okay, well, for this trust domain, I want to believe this root certificate. For this other trust domain, I want to believe this other root certificate, and automatically handle distributing that information around the clusters. So that Federation API makes it much like the sort of chaining up to a root is largely about making it less painful to delegate that signing authority. So you can have some root that you hide in a vault or something like that, and it never has to change. But when we build these APIs that allow us to have more agility around building and distributing these chains of, or these roots of trust, you don't necessarily have to go to that common root model in order to get the functionality that you want, which is sort of distributed signing of certificates. That's my view anyway.
Istio is already has support for multi-cluster meshes and trust domains that span multiple clusters. So while the Kubernetes native primitives are very cluster-centric at this time, they are capable of being bootstrapped into higher level systems that support trust domains that span many clusters.
We got the lights, so I think that is the end of our sort of public Q&A, but I'll at least be up here if you want to come up and have any chats.